We are looking at the top of page 94 in the workbook. And this is an introduction to the last convergence test of section 8.3, the ratio test, which gives us one more way to decide whether or not a series converges. Okay, so here's kind of how this test works. We're going to start with a series, AN. And to do the ratio test, what you do is you start by taking a limit, the limit that you see here. And it's kind of an unusual limit. It's the limit of the ratio between the n plus first term in our series, that's the an plus 1, over the nth term in our series. Okay, so we're going to calculate that limit, and we're going to get a number r. And depending on what that number r is, we're going to be able to tell whether our series converges or not. Okay, and there are actually three different categories here, depending on what the value of r is. So part A, suppose that you take that limit and your r is between 0 and less than 1. Turns out, in that situation, your series is going to converge. Okay, that's one possibility. Another possibility is maybe the r that you calculate when you get that limit is bigger than 1, and in that case, it turns out that the series diverges. Okay, another possibility, the third and last one, is what if you get 1 when you take that limit? Well, unfortunately, in this case, it turns out we don't get any information at all. The test is inconclusive, which means that the ratio test would not help us to determine whether the series converges or diverges. Okay, I want to make one observation about this test before we do an example. If you look at part A and B here, does that behavior remind you of anything that we've talked about earlier in the course? Okay, convergence if r is less than 1, divergence if r is greater than 1. That sounds a little bit like the geometric series test. Turns out there's a very strong connection between this test and a geometric series test, and that's kind of emphasized in this note that we see here. Okay, when we take this limit, we're really taking a ratio of an plus 1 over an, so the r that we're calculating is like the common ratio in some sense. So we could say that by saying that for large n, the series is approximately geometric with a common ratio of r. That's why, when you look at parts A and B, it kind of reminds you of what's going on with a geometric series. Okay. So there's kind of our introduction to the geometric series test. Let's use it to test a series for convergence. Okay, so example 9, they're giving us a series that looks like the sum 3n squared over n factorial. There's that n factorial we talked about a minute ago. And the notation is a little bit of a challenge to get used to here when the first time you do a ratio test problem. So I'm going to remind you that when we say an, we're just referring to the nth term in the series. And when we do this test, we're not only worried about what that nth term looks like, we're also worried about what the term that comes after it looks like, an plus 1. What do we mean by that? Okay, well, an plus 1 is just like taking the term that we started with and just substituting in n plus 1 everywhere that you see an n. Okay, so we'd take every n that we see and just put an n plus 1 in place of it. And so an plus 1 actually looks like this. 3n plus 1 squared over n plus 1 factorial. Okay, now we are ready to actually do the ratio test. Okay, so we're going to take the limit as n goes to infinity of the absolute value of an plus 1 over an. Okay, and we wrote down above what an plus 1 and an look like. So starting with an plus 1, we got 3n plus 1 squared over n plus 1 factorial. We need to divide that by an, which is the same as multiplying by the reciprocal of an. So we're going to take this 3n squared over n factorial and just flip it. Okay, and there's the rest of our expression. Okay, and the rest is algebra. Okay, seeing if we can actually take this limit. One thing that you might notice immediately is that those 3's cancel out. Okay, and then to make the process of taking this limit a little bit easier, I'm going to kind of rearrange it so that things that look alike in the top are over things that look the same in the denominator. You would not have to do this step if you didn't want to. It just makes maybe a little easier to do the algebra. So I'm going to take the n plus 1 squared and put that over the n squared that's in the denominator. Okay, and then take the n factorial and put it over the n plus 1 factorial in the denominator. Notice that all we did was just reorder the terms a little bit. So what we have down here on the second line, that's exactly the same as what we have above. We just chose to write the terms in a different order. Okay, and then we come to the factorials. Okay, so I'm going to rewrite the first part of this. And remember what n factorial means. Again, it's just notation for a big long list of numbers starting at 1 and continuing to multiply until we get up to n. In the denominator, what would this n plus 1 factorial be? Okay, well, that's also a list of numbers that starts at 1. It just continues until you get to the number n plus 1. Okay, and I'm going to make one other observation that's going to make this easier for us. Okay, there's a big ... here, so there's a bunch of terms that we're not writing down. My question to you is, what is the term in this ... that comes right before n plus 1? Okay, well, that number would have to be 1 less than n plus 1. It's going to have to be n. Okay, and so notice, if you make that observation, something kind of nice happens here. We've got a 1 times 2 times 3 up to n in the top and the bottom, and so those two things actually cancel. All of these terms cancel with all of those terms, and all that's left in the bottom is the n plus 1 down here. Okay, so if we rewrite that, making this observation, we've got n squared, everything else canceled except for the n plus 1 down there. Okay, so we have greatly simplified our expression by making that observation and canceling. Notice that there is one other thing that cancels. We've got an n plus 1 squared in the top and an n plus 1 in the bottom. Those cancel and just give us a single n plus 1 in the top. Okay, so we'll rewrite that. Okay, and at this point, I'm going to also drop the absolute value signs because you might notice that everything that we're working with in our limit is positive anyway. N plus 1 is positive and n squared is positive. We don't need those absolute value signs. Okay, and so all that's left here is to take this limit. Notice that this limit has the form infinity over infinity, so we can use L'Hopital's rule on it. And derivative of n plus 1 is 1, and the derivative of n squared is 2n. So we're taking the limit as n goes to infinity of 1 over 2n, and that's going to be 0. Okay, the top is constant, the denominator goes to infinity. And so that 0 that we came up with, that is the number that we're calling r in the ratio test. All right, and so now it's a matter of looking at the ratio test and asking, what category are we in? Okay, so I'm going to scroll up for just a minute here so we can see that. Okay, and ask yourself, we just calculated the value of r and got 0. Which of the 3 categories are we in? Okay, notice that that's category A if r is equal to 0, and so that tells us that this series should converge. Okay, scroll down, and the last step is to just write our proof. Okay, and the good news is, even though the algebra that we did was quite a bit of work, the proof is actually pretty short. All we really have to say is, since we got an r of 0, which is less than 1, our series has to converge by the ratio test. Okay, and again, instead of rewriting the whole series, I'm just going to say the given series converges